Welcome to the Factorization lecture. Across this video, we will go from spotting common factors all the way to cracking tough quadratics. Keep a pen ready, as there are 3 practice checkpoints. In this video, we have 3 main goals: understanding what factors are, extracting common factors from expressions, and factorizing quadratic expressions. Every technique will be demonstrated through worked examples. Here is our roadmap. Part 1 covers common factors. Part 2 looks at quadratics, where the x-squared coefficient is 1, and Part 3 tackles harder quadratics. Remember to pause and try the practice checkpoints after each part. We begin with Part 1. We will start with basic numbers, then apply that same logic to algebra, finding what all terms share and writing that common factor outside a bracket. A quick recall from arithmetic: a number is factorized when it is written as a product. For instance, 15 equals 3 times 5, so 3 and 5 are factors of 15. Algebra works the same way. 16 can be written as 8 times 2, 4 times 4, or 16 times 1. Factorization is not always unique. Keep this in mind, because algebraic expressions behave the same way. Consider the expression 5x plus 20y. Both terms contain the number 5, which makes it a common factor. Spotting this shared term is always our first step. We can write that common factor outside a bracket. 5x plus 20y becomes 5, multiplied by the bracket containing x plus 4y. Always use the expansion check to verify your answer. Think of this as a two-way street. Removing brackets takes you one way, while factorizing moves you back the other way. Because these are inverse operations, expanding is the perfect way to verify your work. Common factors are not restricted to numbers. In x squared plus 2x, both terms contain x. This factorizes as x times the bracket containing x plus 2. Let us look at our first full example, 3x plus 12. 12 is 3 times 4, so 3 is common to both terms. Pull the 3 out front and you get 3, multiplied by the bracket x plus 4. In this second example, 15x squared can be split in many ways. All the products shown here are valid factorizations. Which one you choose simply depends on the specific problem you are solving. For 8x squared minus 12x, both terms can be written with 4x as a factor. We pull that 4x out to get 4x, multiplied by the bracket 2x minus 3. Always aim for the largest shared factor. When dealing with powers, like in 5x squared plus 15x cubed, we take the lowest power. Here, both share 5x squared. Watch out not to lose the 1 when dividing 5x squared by itself. When scanning 3 terms at once, the method remains the same. 6x, 3x squared, and 9xy all share the factor 3x. We pull it out to complete the factorization. Make it a habit. 1. Find the biggest number that divides every coefficient. 2. Take the lowest power of each letter present everywhere. 3. Expand the bracket to check. The example shows all 3 rules in action. Checkpoint 1. Pause the video here. You have 5 expressions from exercise 11.1. Your task is to find the common factor, write it outside a bracket, and then expand to check your result. Here are the solutions. Notice part E. 2x comes out, leaving 2 minus 3y inside the bracket. If you wrote an equivalent form, simply expand it. If the original expression returns, your answer is correct. Part 2. Here, we define quadratic expressions, then learn the sum and product method that lets you factorize them almost on sight. We will cover the definition, the method, worked examples, and the difference of 2 squares. The key point: a quadratic expression has the form ax squared plus bx plus c, where a is not 0. B or c may be 0, but a may not. Otherwise, the x squared term would vanish. Practice reading the 3 numbers. In 2x squared plus 3x minus 1, a is 2, b is 3, and c is minus 1. In x squared plus 7, the invisible coefficients are a equals 1 and b equals 0. All 4 expressions on the top row are quadratics, even x squared plus 7, where b is 0. The cube on the bottom row is the odd one out, as its highest power is 3, not 2. Factorizing a quadratic means expressing it as a product of 2 bracketed terms. Expanding x plus 6 times x minus 3 gives x squared plus 3, x minus 18. Factorizing is simply running that film backwards. When we expand x plus m times x plus n, a specific pattern appears. The coefficient of x is the sum, m plus n, and the constant is the product, m times n. That simple pattern powers the entire method. Here is the recipe. Hunt for two numbers whose sum is b and whose product is circa. Once found, the factorization writes itself as x plus m times x plus n. Always try whole number pairs first. Let's factorize x squared plus 5x plus 6. We need a sum of 5 and a product of 6. 1 and 6 sum to 7, so that is not it. 2 and 3 sum to 5, which is correct. The answer is x plus 3 times x plus 2. Now, for x squared plus 8x plus 12. We need a sum of 8 and a product of 12. Testing the pairs, we find that 2 and 6 sum to 8. The factorization is x plus 2 times x plus 6. For x squared plus 10x plus 25, the sum is 10 and the product is 25. 5 and 5 fit perfectly. Since both brackets are identical, we write x plus 5, all squared. This is called a perfect square. Example 8 is interesting because the x term is missing. That means b is 0, so the two numbers must cancel each other out. 11 and minus 11 multiply to minus 121. The answer is x plus 11 times x minus 11. The pattern behind that last example is the difference of two squares. X squared minus y squared always factorizes to x plus y times x minus y. Expanding it shows why the middle terms cancel. Learn to spot this shape instantly. Let's see the difference of two squares in action. By rewriting each term as a square, the pattern becomes clear. For instance, 16x squared minus 1 is 4x squared minus 1 squared. This leads directly to the sum and difference of 4x and 1. When coefficients are negative, stay calm. In this example, the product is 6 and the sum is negative 5. A positive product with a negative sum implies both numbers are negative. Therefore, negative 3 and negative 2 are our pair. Use this table as a sign detective. If the product is positive, the signs match. If the product is negative, the signs differ, and the larger magnitude takes the sign of b. This systematic check makes guessing numbers much faster. Checkpoint 2. Pause and try these 5 quadratics from exercise 11.2. Hunt for the sum and product pair for each. Remember to be especially careful with the signs in the final 3 problems. Here are the solutions. Part C uses 5 and negative 3 to sum to 2 and multiply to negative 15. Note that part E is the difference of two squares. 100 is 10 squared, so the brackets appear instantly. We now move to part 3. When the leading coefficient is not 1, the problem gets a bit tougher. We must work through combinations systematically until the middle term matches our target. The strategy is to list all factor pairs of the first term and the constant, then test combinations. Speed comes with practice, but a helpful tip is to extract any common numeric factor first to keep your numbers small. For 2x squared plus 11x plus 12, the first term only splits as 2x times x. 12 has multiple pairs to check. Our goal is to find the pair that results in a middle term of 11x. We test and reject until we find the match. Trying 2x plus 12 times x plus 1 gives 14x, which is wrong. Trying 2x plus 3 times x plus 4 gives us exactly 11x. Success. Always shrink the problem first. In 4x squared plus 6x plus 2, every term is even. Extracting the 2 leaves us with a simpler quadratic inside. Don't drop that 2. It must remain in your final answer. Worked example 12 has more moving parts. With 6x squared, we have 2 different ways to split the leading term. One failed trial shows why we must be thorough. Finally, 3x minus 1 times 2x plus 3 hits the target. Honesty in mathematics. Some expressions cannot be factorized. X squared plus x plus 1 cannot be split using whole numbers. Identifying that an expression is irreducible is a valid and important skill. Later methods will handle these. Checkpoint 3, your final challenge. Before you calculate, identify the technique required for each of these 6 expressions. Then, pause the video and work through them carefully. Here are the final solutions. Each is tagged with the technique used. Remember, you can always verify your work by expanding the result to see if you return to the original expression. To wrap up, factorizing is writing products, and expansion is the ultimate test. Follow the hierarchy. Common factors first, then specific patterns like the difference of squares or sum and product. Practice these, and you will master factorization. Thanks for watching.